Howdy everyone, and welcome back to my channel, and welcome back to my lecture series on on solar systems specifically, astronomy in general. I do apologize if you have been following along. I haven't been online for the last 2 weeks due to health issues and due to spring break and things of that nature, both boring and mundane. For those of you who are watching this in the future, it's not really a problem. So anyway, what was I going to do? So I need to actually send out, I was going to send out notifications because I don't think I actually managed to tell my students that I'm doing this. So if you'll bear with me for a second, I am going to find my find the link to this. Copy. There we go. Put that there. And let's tell folks over at Blue Marble Science. All right. Enough of that. So, all right. Nope, that's all I wanted. That's what I wanted. All right, so let's get started. So today's lecture is about recording data. And I'll also throw in a little bit of a discussion of a spectrograph, which is a particular type of instrument that we use to collect and create and record astronomical spectra, something I've talked about in previous lectures and how very important it is. And I'll go over the simple design behind what a spectrograph. Spectrographs can come in all sorts of shapes and sizes, and they can get quite complicated. All right, so let's bring this up. I do apologize for the crudeness of this model, as today has been a bit hectic, but it has, I think, all of the information that we need. So let's first start off with the first detector that we have, and I'll introduce two particular quantities that I will refer to when dealing with the various detection systems that astronomers have used over the ages. Now, obviously, Galileo onwards for till I want to say the late 1800s, mid to late 1800s, astronomers used their eyeball. And what we see here as the eyeball is a combination of both a telescope and detector. So it's you can think of the eye as a very simple telescope where you have a lens that collects the eye through the pupil and then focuses that light on the retina. So what we have here in terms of looking at this from an astronomical point of view is that you have the iris. The iris sets the aperture, or essentially how much light is allowed to hit the back of the eye. Now, fully dilated, and on the right drugs, the human eye, on average, gets fully dilated to about 8 millimeters. So you can go back and you can work out what the angular resolution of the eye is and the light collecting area is, at least in comparison to, say, a 1 meter telescope. Excuse me. So you can tell that it's very, very small. It's very, very small. So the iris controls the aperture. You then have the lens, which obviously is what focuses the light onto the retina, which is the detector. And then then that information is then sent to the optic nerve, which you can think of as a USB cable or any excuse me. Still recovering. Georg. Hopefully I pronounced that right. Howdy. So anyway, the optic nerve is the basically the USB that sends the information to your brain, which is the computer, which analyzes the data, and we interpret it as light, or we interpret it as visual information. So there are two things we need to discuss in terms of judging the quality of a detector. There is something called the integration time, and then there is something called the quantum efficiency. The integration time, simply put, is the amount of time that the detector receives light before it downloads essentially that information to the computer. You can think of it as a shutter speed. So the integration time for everything else that I'm going to be talking about can be adjusted anywhere from a split second, maybe a half second, to hours upon hours. It really just depends on what you need to, what kind of science you want to do with that particular detector. The quantum efficiency is a fancy term to indicate how efficient or how well a detector actually captures light. And we talked about that light can interact with matter in 4 different ways. One of them is through absorption. The matter can absorb the light, and also through transmission. The light could actually can pass through the material or the matter if the situation or the material is, the circumstances are correct, or the circumstances are amenable to that. So quantum efficiency deals with the idea of, we refer to quantum efficiency in terms of a percentage. What is the percentage of infalling light that is actually captured by the detector and sent to the computer? So a quantum efficiency of 50% means that half of the photons that hit the detector are sent to the computer, and the other half are basically pass through the detector and get absorbed somewhere else. So that is tied into, hopefully you can see that is sort of tied into the integration time, because what we need to do is we need to be able to collect enough what we call signal or light from the objects in order to enough light in order to see what we're doing and to see the astrophysical phenomena we're trying to analyze. And we need to do so above a background noise. So any sort of electronic device is going to have a certain amount of noise associated with it. Even photographic plates, I would imagine, also have a certain amount of noise. But with the eye is very good at a couple of things. The eye is very good at quantum efficiency. I don't remember off the top of my head what the quantum efficiency of the retina is, but it is rather high, fairly close to 100% if memory serves. And it is very good at, it has a very high dynamic range, which I guess is another thing that I'm going to be talking about to a certain extent. Dynamic range is a fancy way of saying the ability to distinguish the brightest brights from the darkest darks. So the human eye has an extremely high or extremely large dynamic range, so we have a lot of contrast in the things that we see around us. And like I said, a lot of the light that hits our eye actually gets captured by the retina and registered by our brain. The thing that the human eye kind of sucks at is obviously the pupil size is fully dilated, is only around 8 millimeters. So the amount of light that the eye collects is pretty limited. So our angular resolution is very bad. We cannot see fine detail at even modest distances on the Earth. And we are limited to how bright or how dim an object we can see. And that, if from an astronomical point of view, is about 6th magnitude, depending on the eye. So we are limited by the eye, our visual observations, to without the use of a telescope, to only objects that are 6 magnitude or brighter. Obviously, with a telescope, that allows the eye to collect more light, but with the unaided eye, that's where that is where we are at, assuming that there is no light pollution, which that's not going to happen, or very rarely going to happen. Now, from an astronomical point of view, like I said, during the advent of the telescope, which was in 1609 by presumably by Hans Lippershey, at least by our best estimates. From 1609, like I said, to the late 1800s or mid to late 1800s, the human eye was it. That's basically the only collection device that we had, and there's a lot of ambiguity with the human eye, which I am going to talk about later tonight at the Evening Under the Stars event, which I will talk about or hawk at the end of this lecture. So there's a lot of ambiguity. Obviously, when we look at something, our conception of it, our interpretation of it, is subjective. When I look at something, I might see something slightly different, or in some cases, very different than when someone else looks at it, particularly if we are looking at very dim objects or very small objects. Excuse me. So while the human eye did allowed us to do a great many things, it allowed Galileo to see the moons of Jupiter. It allowed to see the motion of the moons of Jupiter. It allowed him to see sunspots, the phases of Venus, and all that. It was really the way that he recorded the data was simply by hand, which again is very subjective. So what happened in the mid 1800s to late 1800s? Well, photography happened, and specifically, photography was then used for astronomical purposes. This is a photograph of the moon taken what we call with a photographic plate. Now, I have, in a previous stream sometime, I can't remember where, I actually have shown these, but I have a collection of photographic plates, which I may or may not have stolen from my previous place of employment. And so this is a rudimentary photographic plate. This is basically what we use. It's 8 by 10, thereabouts, basically the size of a piece of paper, and it is a piece of glass. It was, in order to see the image, we used a substrate of silver hydride or something of that nature, and then we developed them in darkroom. And what hopefully you can see is this is a image of the Ring Nebula, which is a planetary nebula. Essentially, this is what the sun is going to look like in about 4.5 billion years or so. So you can see this ring of gas, which has been ejected from a central star, which is now a white dwarf, which is located in the center of the image. So we were able to take this and image this onto a photographic plate. The main advantage of the photographic plate was the fact that the observations now are no longer subjective, and we have the ability to record those observations in perpetuity. For example, Harvard University has the largest collection of photographic plates in the world. So if you are looking for an astrophysical phenomena, or looking at an astrophysical phenomena, such as what is now known as Boyajian star, this is a very, very weird star, which again, I will be talking about later tonight. This is a very, very weird star. And what we wanted to know was, what is this star weird now, or was it weird or has it been weird all the way since we first looked at it? And one of my colleagues actually went to Harvard, looked through the photographic plates, did the measurements, extracted the data on this star over the past 100 years. Now, the data was sparse. The observations were spaced out pretty well, or spaced out pretty. There was a lot of time between each individual observation, is what I'm trying to say. So all he could really do was he found essentially just a general trend of how this star was brighter, or general trend of the brightness over time, and as he found, it was actually slightly decreasing. So we would not be able to know that if we were still left with visual observations, because the ability to make fine measurements can only be done with a physical medium such as this. So because of the subjective nature of the human eye, determining the brightness of something is very, very crude. So we need something. So the main advantage of this kind of detector is that it allowed us to make more precise measurements and to keep those measurements in perpetuity, so that we can look back and see what an object might be doing over a much larger time frame than, say, our lives, or certainly over our graduate career. The problem is that that photographic plates have a fairly low quantum efficiency. When they first came out, the quantum efficiency of a photographic plate was about 10%. Or for every 10 photons that hit the photographic plate, only one of them was registered. Now, as photography advanced, we got up to about 50% in terms of quantum efficiency. What this means is that you had to integrate over a much longer time frame than we do now, because of the fact that we aren't capturing light efficiently. And what we want is, again, we want to be able to build up this signal. We want to be able to get the brightness, or get the information, the light coming off the star, at a level that is above any kind of background noise or background brightness, so that we can see details like we see in this image of the moon. Also, photographic plates, anyone who's done any kind of photography in a darkroom, you know that it is a slow process, both, like I said, in integration time and actually processing time, and it is messy and potentially hazardous. The emulsions used to develop these plates are what's the word? I keep losing my words. Are basically biohazards. You can get sick if exposed to them in large quantities, and so forth. Howdy, Clive. No, you have not missed the alien pics yet, but they may be coming later. So we had photographic plates. That ended around the turn of I want to say 1970s. 1970s, there was something known as a tool that was developed called a photomultiplier tube. Now, with photographic plates, what we see is an extended image. You can think of this as a brightness distribution over an area, light over a set area or field of view. A photomultiplier tube, which had a higher quantum efficiency than the photographic plate, was limited in that it did not image things. It's essentially a photon counter. And not to really go into the weeds of this, but essentially what happens, in order to get this better quantum efficiency, a photon was captured and it then hit certain diodes and anodes, and was able to basically produce more electrons, and eventually those were captured captured at the back end, and that allowed even just a small amount of photons to be detected efficiently. But like I said, it simply counted the number of photons. It did not image anything. Now, this is good for this is adequate for the field of photometry. Photometry is simply the measure of how bright something is over time. So a photomultiplier tube did a adequate job in doing that. You pointed it at a star, you got a number of counts over time, and then you can convert those counts into a magnitude, into a brightness. And a gentleman by the name of Arlo Landau was able to set the standard, or basically set the standard of how bright these things were, and he used a photomultiplier tube in order to do it. The quantum efficiency for the photomultiplier tube, like I said, it's around 70% if memory again serves. But that brings us to CCDs. Now, a CCD, or charge coupled device, is the modern method via which we take data. It is the same device that is in your phone. So your phone camera has a chip, which is, like I said, called a charge coupled device, or CCD. Now, there are a couple of differences between your camera phone and what we use from an astronomical perspective. In brief, or in general rather, and this applies to both astronomical cameras and digital cameras, you can think of the chip as an array of rain buckets, or photon buckets. And so the photons come down, hit this pixel basically in the same pattern as the field of view that the telescope is looking at. So if we were to look at the moon, for example, the image of the moon would then be imaged onto the camera, and each of those little bits of light and the moon would hit a very individual pixel on the chip. So that and then that data, or those photons would be collected by a substrate, and then through electronic means those photons, or those electrons, through the photoelectric effect. So let me back up a moment. The way this works, super huge the way this works is, so a photon hits a substrate, typically made out of an alloy, or hits a substrate made out of gallium, among other things, and through the photoelectric effect that Einstein got his Nobel Prize for, the photon hits and it ejects an electron. That electron gets captured by an electrostatic force, and that then gets translated out off the chip onto the computer, and is read as counts, or basically the number of photons that hit it. Hopefully that makes sense. So essentially, it reads the number of electrons that got liberated from the gallium due to the photoelectric effect, and it transforms those into counts, very much like the photomultiplier did. Something else I wanted to say, but it just completely escaped me at this point. So, again, the quantum efficiency here has improved, and the quantum efficiency now for state-of-the-art cameras is around 90% in the visual out to the red. In the bluer part of the spectrum, and the bluer part of the range, and the near ultraviolet part of the range, the quantum efficiency drops fairly significantly, down to about 50 or 60%, depending on the type of camera being used. So while the CCD is much better than the photographic plate, and markedly better than the photomultiplier tube, we do still lose a lot of light in the bluer end of the spectrum. Guess whose birthday is also on Sunday? This guy's. That's right. I have the same birthday as Leonard Nimoy or Spock. Granted, He was born earlier than I was by a few decades, but yep, I share Spock's birthday. Really wish that meant I was as smart as Spock, but it's still nice to have that kind of coincidence. Anyway, where was I going with this? So the quantum efficiency, like I said, is leaps and bounds. So when we go back to this image of the moon, this image might take you take you an hour in order to capture with a photographic plate of the full moon. You can then take a full picture of a full moon with a modest telescope, the smaller telescope, in the matter of minutes, and you can do it in color. This brings us to the main difference between a camera phone or normal typical CCD cameras or digital cameras and astronomical cameras. Digital cameras, the chips that you see, basically the pixel, is actually subdivided into 3 pixels: something that is sensitive to blue light, something that is sensitive to green light, something that is sensitive to red light. And when it reads out that chip, you have 3 color information built into the data. And so you can combine, so the camera can then just combine that into a true color image. So you basically get an image of exactly what you see in the real world. Now, astronomers are much more interested in actually analyzing the light in those specific colors, and blue and green and red and so forth. So what we do is we use our cameras are monochrome. They will pick up light from if we're talking about the visible range, they pick up light from the near ultraviolet through blue or through Roy G. Biv, although backwards, blue, indigo, violet, so forth, out to the near infrared. And so it collects all of that light. In order for us to signal out or weed out only that light we are interested in, we put a filter or piece of glass in front of it. And that filter, that piece of glass, has been coated such that it only allows light through of certain wavelengths. So it only allows blue light to go through, or green light to go through, or red light to go through. So when we create these images, these color images that you see through, oh, hey, Lonnie, when you see these images from Hubble, when you see these images from JWST, what that is essentially a combination of light in a blue filter, in a green filter, and in a R filter, red filter. Now, because of the way those filters are designed, all of those images that you see in Hubble, in JWST, all of those images are false color. If you are in the Starship Enterprise and you are in front of the pillars of creation, they would not look like the pillars of creation as captured by Hubble. The reason for this is that we are interested in the science of the light, not really the pretty pictureness of the light, or trying to get a accurate visual representation of what these objects look like. So the filters are specifically designed to look at interesting wavelengths from an astronomer's point of view. And what I mean by interesting is wavelengths that will allow us to use various methods to take the light in those various filters and derive astrophysical parameters like temperature, roughly composition, mainly temperature and energy, that sort of thing. So, and with JWST, that CCD camera is actually very sensitive to only infrared. Rather, their main camera is only sensitive to infrared. It actually doesn't look in the optical at all. And so when the images that you see from the JWST, those are certainly false color, because if you were in the Starship Enterprise and you wanted to see in the same wavelengths as JWST, well, you couldn't, because they are beyond the range of the human eye. So I want to put that out there. I want to have a what is the word? Sort of a I forgot the term, disclaimer. A disclaimer that basically says those images are false color. They're not false. They are truly images of the various astronomical phenomena, pillars of creation, the whirlpool galaxy, so forth. But they are not the same color as if you were to go there and actually look with your human eye. And as I said, when we look through the various filters, we can then combine the light and figure out certain things like temperature, for example. I'll talk about something called a color index. When we use a color index is when we take the magnitude of an object in the blue filters minus the magnitude of the object in the green filter. That tells you something about the temperature of the star, because if you remember from the black body curves in a previous lecture, you're sampling at two different parts of the curve, meaning that you get a different amount of light based on the height of that curve. And that curve is dictated by the temperature of the object. And so B minus V is a very crude way of being able to tell the temperature of a star, for example. Oh, thank you, Limey. I'm excited. I have the same birthday as Spock. So now, in the announcement for this, I said I was going to show you what the first CCD image of an astronomical body, what it was, or what was it astronomers wanted to look at so badly. Now, double checking this, I actually was wrong in my first assumption, but I think it's the second image that was taken, or at least made public. So I'm gonna put out there in the chat. Make a guess as to what the first astrophysical object that was imaged through a CCD, what that was, and what it was the second one. And why I tell you that, I will say it's aliens. No, it's not aliens. Oh, and today's lecture is brought to you by Toblerone, makers of fine chocolate everywhere. One of my students gifted me this. Oop, that's not what I wanted to do. That way you can see my, beautiful face. Meteor than Groot? No. All right. I won't keep you in suspense any longer. Let me see if I can do this. Share screen. The moon. There. The moon. The dome of the Andromeda Galaxy. No, it wasn't Andromeda. So the first thing they looked at in 1974 was the moon's surface. This was the first ever astronomical image taken by a CCD. And here you can see, I really wish it was the Mass Effect. Great game. One of my favorites, the Mass Effect series. Here you're looking at essentially a field of view, or a camera rather, that is 100 pixels on 100 pixels per size, or 0.01 megapixels. So you can compare that to modern cameras. Obviously, this is actually rather small. Here we have another consequence, or another limitation, that a detecting device adds to the situation. So, as I've already talked about, the angular resolution, or the amount of fine detail that you can see, is limited by the telescope's aperture. But it is also limited by the pixel sizes or the number of pixels that you use if you were using a CCD camera. So obviously with that first image, there weren't a lot of pixels. The pixels were very large, and so your angular resolution degrades because of that. And I just played through that trilogy a couple months ago. So we can compare this first image in 1974, to more modern images, and you can see that these are. This was taken with the Hubble Wide Field and Planetary Camera, and it's 100 or 800 by 800 pixels. Even it's still very crude by today's standards, but you can see the enhanced resolution of the lunar surface just by making the CCD camera have smaller and more numerous pixels. Now, this is what I thought the first image was, but I was wrong. What I'm about to show you is the first image taken of that object. So, in 1976, the year of Moi's birth, dating myself, the first ever image of Uranus was taken. Not entirely certain why they went with Uranus rather than anything else. Probably, my guess is because it was far away and they were testing the limitations of their device. And so this is an image, a 400 by 400 pixel image of Uranus. It's there. Now, that dark spot that you see in the center of it, that isn't real. That is an artifact of the imaging device. Not entirely certain what that artifact is or what is causing that artifact. I would have actually expected it to be the other way, where it would be bright in the center and dim on the edges, possibly due to vignetting. But there is obviously a dark spot here, and we know from Hubble that that spot doesn't exist. So when you're looking, this is kind of a word of warning. When you are looking at images, you always have to keep in mind that there may be errors in your image, particularly if you're looking at something that is very faint or very, very small. There is noise to consider when you are taking these images. And like I said before, what we want is a lot more signal or a lot more light from the object that we want. A lot more light than we get light from noise. So I would imagine that the signal to noise of the Uranus image is much larger or much smaller than the Hubble image. And this actually apparently is true color. I don't know about that. I didn't think that Hubble was able to do a true color image, given the filters that they have. But that's probably a little bit nitpicky. So yeah, that is a CCD camera. I think that is all I really wanted to say on this. Oh, real quick, and I apologize. This is getting a little scattershot. Now, when it comes to integration time, we would like the integration times to be as small as possible or as short as possible. And the reason for this is because the tracking of a telescope is never perfect. It can be very, very bang on. It can be the accuracy can be within arc seconds, but it's never perfect. What that translates to is a error in your tracking. And if your error is, if you don't track perfectly, if you expose for a very long time or a long time, then your object of interest can actually move inside that field of view. And if it moves, then it's going to blur out and it's going to basically cause a distortion. So we want to be able to minimize the amount of time that we look at an object to really mitigate that any kind of tracking error that may exist in the system. So that's why we want more better quantum efficiency than anything else. Oh, proper astronomers make observations with P1000. Yeah, true. Hopefully they actually have it in focus. All right, and so the last thing I want to talk about in terms of this. Nope, wrong way. There we go. Is a spectrograph. Now, a spectrograph is a more complicated, or is an instrument that is used to split the light into its component colors so that we can get those nice astronomical spectra that I talked about before. With a CCD camera, just a CCD camera by itself, we can mount that at basically the point of focus for your observing instrument, be it any kind of telescope that you have. Or again, with a phone, whatever lenses that you happen to be using. And so that's it. You just mount the CCD, you mount some filters in front of it so you can figure out, you can look at very specific wavelengths. A spectrograph uses a CCD, but it's again a little bit more complicated. What we do is we take the light that is collected from the telescope, we then send that light through a slit or a small opening, a small vertical opening in a mask. And basically we have a you can think of it as a sheet or a piece of metal or what have you that is square. And then we cut a very small vertical slit in that plate. The reason for this is because we want as concentrated a light as we can possibly get later on down the system. And we can't get that from just looking at the entire field of view. We need to basically cut that significantly. And what this does is it significantly limits how much light we can gather at the back end. So not only do we have to worry about the quantum efficiency of the camera, but now we're not getting the full light we're not using the full aperture of the telescope, essentially. So we are now much more limited in how much light we can collect. So spectrographs or spectroscopy is what we refer to as observationally expensive, meaning that you have to integrate much longer in order to get good data than if you were doing simply photometry. But as I've mentioned before many times, spectroscopy can give you a wealth of information about an object, its temperature, its composition, its motion, things of that nature. So it is worth it to do it. Well, anyway, we send the light through the slit. That hits a mirror, which collimates the light. So coming out of the slit, the light is diffracting. It'll hit this mirror. It then takes that light and collimates it. Basically, it turns it into plane parallel waves. Those plane parallel waves hit a diffraction grating. You can think of it as a really fancy prism. That will split the light into its component colors. It will then hit another mirror and then get reflected back onto a CCD, and we will literally image that spectra, that rainbow pattern of colors with dark lines running through it, or a spectrum of bright lines running through it. That will then get downloaded to the computer, and then we can take that image and analyze it in order to determine what the intensity of the object is as a function of wavelength. Spectrographs are very sensitive instruments. You need the alignment of all these different pieces of glass to be perfect. If anything is out of alignment, then things get blurred out. You lose information, so they need to be perfect. So typically, research spectrographs are in their own room. They are not mounted on the telescope. They're actually in their room, what's known as a coude room, beneath the telescope, and light is then shunted down into that room. Now, there are spectrographs that are actually mounted to the telescope. No, I'm going to back that out. Research-wise, the spectrograph is always going to be in a room upon itself. And sometimes that light is directed by mirrors, and oftentimes now it is directed through fiber optics. But like I said, that gets into more specifics that I really want to deal with at this level. All right. hopefully that all made sense. I do apologize today. Like I said, today is a bit hectic. I feel like I'm all over the place. But those are the instruments that astronomers have used and continue to use today to do photometry, to make images of the night sky, and also to create spectra of the night sky. Excuse me, still congested. Let's do that. Nope. Let's do that. I can tech. All right. So now, so it does have a yes, a spectrograph in fact does have a container. And I would go so far as to say you can only do spectroscopy if you have a container. Because if you don't, then you're going to get stray light into the optical system, and that's just bad news bears. So, yes. So spectrograph requires containment. Requires a container. All right. So now I'm going to... so I mentioned before that I'm giving a talk later tonight. It's part of our Evening Under the Stars series, which I hope I've mentioned before. But here at GMU, George Mason, we do most every other Tuesday, although scheduling is a bit weird. Most every other Tuesday, we have a public night here at our observatory, where we bring in a speaker who is typically an astronomer or someone related to astronomy communication, or a very dedicated citizen science scientist who does work, does serious work in astronomy, or assists serious work in astronomy. And we have them give a talk for about 40 minutes. We have a Q&A session, and then folks can then walk over to our observatory, and then they can look through our telescope through eye. We also, because of the pandemic, do this virtually. So it's a hybrid. So we have people in person, and then we also have people who can join digitally. For the digital folks, they can obviously hear the talk, see the talk, and then afterward we give a virtual tour where we have webcams which show the telescope, and we can also share our screen and let you see the actual interface that we use to control the telescope. I will be doing that tonight. Normally I MC, but I will actually be giving the talk tonight. And so if you are up at that hour and you would like to see me give a talk, then I encourage you to go to this website. And down here, there is a Zoom link right here, which you can then, there's no registration, no hoops to jump through, other than having Zoom and presumably having it update, because it always updates. Click on the Zoom link and you can join us. Now, this is, as we put up here, and wow, as a good astronomer, we actually included the UT time. So we have, it starts 7 p.m. Eastern Daylight Time, and because daylight savings is a thing here for some reason, UTC, it would be, it's actually going to be at 11 p.m. UTC for all of you international folks. So again, what I'm going to be talking about, and obviously you can see the abstract there, what I'm going to be talking about is where science fact or scientific observations have been taken that are very strange, and the investigator actually goes to aliens or science fiction to explain it. So this is right up Clive's alley. So I'll be talking about three particular instances where the primary investigator looked at a set of observations and said, "Yep, aliens," in a serious way, and a couple of them actually held to that and still hold to that belief to this day. So if you'd like to see my give a talk about science and possibly aliens, please feel free to join me there. So Yeah, Limey, I hear you. My sleep has been for shit the last couple weeks or more. So I perfectly well understand if you can't join me for that. But it is recorded. It is, and the recording will be uploaded onto our Evening Under the Stars YouTube channel. Something that I've been trying to do and not being up to date with is I take the data file and cut the talk portion of it out and post it onto my channel. I've only done that once, maybe twice so far. So that way, if you're just interested in the talk, then you can just go to my channel and watch it there. Stop. No, I want to do that. Excuse me. Like I said, still a bit congested. And so again, the Evening of the Stars starts at 7 p.m. Eastern Daylight and 11 p.m. UTC. The channel, so we have, obviously there's my channel, but if you want to watch the recording later on, it is just simply, you can just simply look in Google or look in YouTube. Just George Mason. Whoops, sorry, nope, that's not right. Here, let me just find it. George Mason Observatory. Where's our? There we go. Copy and paste. There you go. So that's the YouTube channel for our observatory. I help maintain it, but I am not the only contributor. So you can also watch previous Evening of the Stars that we've done. We've done this for a couple 3 years now, where we've basically, since the start of the pandemic, we've done these events virtually. So we have a host of talks that you can go back and watch. So yeah, and I think there's an observatory tour that that the director, my boss, essentially Peter did. So, all right, if there are no questions, I'm going to leave it at that, and I am going to attempt. It is my intention to try to catch up on my lectures, and so I will be giving a lecture at the same time, 3 p.m. Eastern Daylight, or 11 p.m. or 7 p.m. UTC, every day for the rest of the week. So Wednesday, Thursday, Friday, I will be giving a lecture every one of those days. So, howdy, Space Audit. I believe that's Alan. I believe Space Audits is Alan. So, howdy, Alan. You've kind of come in at the very end of this, but feel free to watch the beginning of it. I talk about detectors. So, are there any questions? I'm going to eat a bit of Toblerone, and if you have, and wait to see if anybody has any questions. If not, then I will sign off. So, yummy, yummy Toblerone. Nom, nom. I know it's riveting to watch me eat Toblerone, but all right, that's all for me. That just reminds me, actually, I may not be doing a lecture on Friday because this Friday, myself, Peter, and a whole slew of students are going to go to the Green Bank Observatory in Green Bank, West Virginia. Now, because of the nature of radio astronomy, we can't basically use cell phones when we're up there, or at least not when we're close to the observatory or close to the telescopes. But I will hope to, I have a hope to actually maybe go live while I'm up there, and at least show you from a distance the the GBT, which does not actually stand for Great Big Telescope. It stands for Green Bank Telescope, the largest steerable radio telescope, tied with the one in Bonn. But the thing is, I will probably be leaving here around about 3 p.m. to make the trip out to Green Bank. It's about 3 hours away from here, and then I'll be coming back on Saturday. So, yeah. So yeah, I will figure it out. I will let you all know if I'm doing it. Limey, if you lived over on this side of the pond, I would drive to you and give you a Toblerone, but unfortunately, I can't really drive across the Atlantic Ocean. What is wrong with flat earthers? That is a question for the ages. That is a very, very complex question. Depends on, I guess, the group of flat earthers that you're dealing with. The Bevites, I think, are just morons. I will just put that out there. I do not believe and trolls. Some of them are very, very ignorant. Well, all of them are very, very ignorant. Some of them, I will go off on a limb and say, have a low IQ. I think you know who I'm talking about. And they're trolls. I think they just want to provoke people into having a reaction so they can feel better about themselves. Alan, a Bevite is anyone who is on the level, or basically, which is run by Bev Try Thinking, and he is not a flat earther, at least by his own admission, I guess. He refuses to be called a flat earther. He believes that if you call him that, he will immediately use the word psyop. What he will say is that horizontal, they're all, I don't even remember how he phrases it. Basically, the Earth is level and is a basically horizontal plane. And you can prove this through the application of Euclid's postulates or axioms. It's kind of ridiculous. To give you an idea, and then I'll shut up about them. To give you an idea, because pi is an irrational number, they have claimed that you cannot accurately measure or calculate an area or calculate a volume. If you use pi, you cannot accurately determine those things. It is, and that's where I say they're trolls, because I cannot believe anyone would have that conception, would basically distrust an area calculation or a volume calculation because it uses pi. So anyway, yeah, so they are something. They are the only flat earthers so far that I have had a very negative reaction with. Well, that's not true. There's a guy named Rodrigo that I had a very negative reaction. But anyway, this is not a flat earth stream, so I will get off that. And I shouldn't be I don't like bad mouthing people, but look into them at your own discretion. I warn you that they are not. I do not think that they have anything meaningful to say. I don't think they have anything that is really meaningful to say on either side of the earth. Certainly not from a globe perspective, and from a flat Earth perspective. I think most flat earthers would think they're crazy as well, or not crazy. They would think that they are misguided as well. So, well, I mean, they said that fairly recently. I've really stopped paying attention to them because basically they actually stopped interacting with me. A couple of them said they would no longer interact with me because of my mental health. So I was like, done. That is a line too far to cross, and so I stopped paying attention to them. But it was fairly recently, I think. I don't know what they're on now. Blue Marble can tell you. Anyway, now that being said, that all being said, I wish you all, I want to end this on a positive note. I wish you all a good day or a good night, depending on where you are. I hope you have clear skies. Remember to look up. Up at some point. The stars are amazing. The planets are amazing. So, peace out, clear skies, and I will see you next time.